Perfect. All right.
Oh,
So,
wow.
morning, everyone. First, I want to introduce my good friend, Gerald Friedland, Professor Gerald Friedland. He's from UC Berkeley, where he teaches a bunch of different things. Anyways, Gerald's a master of many trades, and he's been at the forefront on everything from speech recognition to systems to these days machine learning with neural networks. And so one of the really cool results he's had in recent times was on how to quantify the capacity of a neural network. There's a lot of work on it, and you end up with lots of really ugly formulae, and none of them really tell you anything. So you can go through 30 papers or 40 papers. At the end of the day, you have some math ideas, but then you come back with, what the heck did I just learn, and how does it help me in life? And Gerald's work sort of kind of addresses it head on. So he actually has these very nice information theoretic ways of quantifying the capacity of a network. And he can use these directly to build, for instance, really small neural networks. And in the process, he has this entire theory on reproducibility, experimental design, and so on for machine learning in general. So with that intro, I will hand this over to Gerald. Gerald, the floor is yours.
Thank you so much. So everybody can hear me. I'm gonna add a chat window that helps you to do questions. Where's my chat? Oh, maybe you don't have that here? Let's see. It's a different version of Zoom. Richard, do you know if you have chat? Okay, so everybody can see the slides, right? And then maybe just interrupt me in case, here we go. Here's my chat window. I found it. Stop participates more chat. Here we go. Perfect. Yes. Okay. Yeah. So this is, I learned this is an easier way. If you have a question, just type it into chat. And this way it works. And also sometimes I ask questions or something, you can totally just type it into chat. So yeah, these are slides from a tutorial I gave a couple months ago, a couple of weeks, in fact, it feels to me, but now with all of this is weird because that was actually a real conference with real people in a real location. And it's based off a class that I give at UC Berkeley now, which is experimental design for machine learning. It's a little overstatement because it's some basic methods, but it's mostly concentrated on neural networks, just like Victor said. There's a paper, demo, and all of this, which I right away want you to point to, which is at tfmeter.iscsi.berkeley.edu. You may know the TensorFlow playground, and we took that TensorFlow playground and added a bunch of measurements to it, so you can see all these measurements, all the stuff that I'm basically showing you today. You can just play around with it, and we even, I think, have a student online, Axel, who's part of building this. So thanks, Axel, for joining, and thanks for helping building this. Let's go through this. So that's me. I'm a adjunct faculty at UC Berkeley, a data scientist at National Lab until recently, and then also I started working machine learning in 2001. So I did a bunch of stuff. And one of the things you may see in one of my early stuff was my PhD thesis was to extract foreground and background from images interactively. And this tool is actually, I'm really proud of it because it's still in GIMP. So you can just go and click this button. It may have changed layout slightly and use the tool. And it's also in various other open source tools, including the National Institute of Health has this ImageJ library, is officially medically endorsed image manipulation library where this stuff is in. And I'm super proud of this because it was like an actual product that is used by lots of people. Also, you may have seen 100 million images and 1 million videos, which was the YFCC 100M corpus, which we released. And we did a bunch of multimedia retrieval with it. And one of the big things there was to enable students to be able to do a search on actual 100 million images. And this is a Jupyter notebook showing a geolocation search on this. And I'm introducing this just as my background, but also because that particular thing actually led to the work that I'm going to show you today. Because one of the interesting things here is when you ask yourself, you have 100 million images and a million videos, and what we did is, we called Amazon and said, can we have some EC2 time? And Amazon is super nice to universities, right? So they gave us in $100,000 chunks just EC2 time as we needed, and I want to thank you for this. But also, at some point, you ask yourself, is that actually sustainable, right? I mean, because one of the questions we really need to ask is, how much money, like CPU time, memory I/O, or whatever, do I actually need to budget for my deep learning experiment? And if you look into just computer vision right now, the state of the art basically has no answer, right? You just empirically determine that, okay, let's say AlexNet has 238 megabyte of a model, and it needs like 2.27 billion operations to train. DarkNet is like a second contender, 28 megabyte of a model. And VG16 has 528 megabyte of a model, like twice the size of AlexNet, and it's 30,000 billion ops. So I know these are not the newest state-of-the-art models here, but this is a typical snapshot of how the community currently works. We have some network, it does something, so why don't we all use it? And it's not clear at all how to size or how to actually predict how big something should be. And if you do physics, if you ask physicists, and this is also how it started, is then they'll say, you don't have to be that accurate, but the major point is this is orders of magnitude off. And the moment you are orders of magnitude off, you really can't call this a prediction anymore. So that was basically one of the big incentives to say, okay, is there anything we can do to sort of think about how big does something need to be? And especially when you do large scale experiments like on 100 million images, right? What can we do? So, and I'm going to start this very, very high level, very high level, because what I needed to do in order to answer this question is to basically kind of go back on honestly 20 years of practice of having done this, I mean 19-ish years of practice of having done this, and just go back and say, no, how would we rethink the whole thing? And so I'm going to give you a it's much easier to do this interactively, but we'll try anyway. I'm going to give you a little game. The game is this. If I ask you to continue the first sequence, 2, 4, 6, 8, I'm pretty sure, if I actually asked you on chat, I would see 10. Everybody gave me 10, would give me 10. Now, if you continue the second sequence, 6, 5, 1, 4, that's not so clear, right? What's the next number, right? And more interestingly is I tell you, can you, in the spirit of the first sequence, give me the next number, 100,000? In the spirit of the first sequence, you would say, oh yeah, it's 100,002. But in the spirit of the second sequence, you wouldn't know what the next number for 100,000 is, because you don't know what? Yeah, you don't know the rule that underlies the second sequence. And that's the whole trick. The trick is, when we do machine learning, we don't want to memorize a sequence. When we do intelligence, we don't want to just memorize the sequence. We want to extract an underlying rule, okay? And the underlying rule for 2, 4, 6, 8, 10 is obviously +2, or all even numbers, or whoever you want to call it. You can give it different names, but the major point is you found a rule, and the moment you found a rule, you can extrapolate to unknown, unseen data. But if you are 6514, the only thing you can do is, before you find a rule that makes sense, and by the way, this is the ending of my phone number that's intentionally chosen because it's a unique ID, it doesn't have a rule. If you go 6514, then all you can do is memorize 6514, and you didn't find a rule yet. And so that means while you can memorize 6514, that's something, you cannot find, you don't have a rule to extrapolate to unknown data. And that is basically what we call generalization. The point is 2468, the rule plus 2 generalizes, and not having a rule for 6514, all you can do is memorize. And this is basically the major trick we're going to go through. We're going to figure out if neural networks are memorizing or generalizing. And of course, you all know a technique for that, which is actually to present a validation set and then try this out. But the question is, can we do this in a different way, not post hoc, but before that? So the next thing is also for me, and again, it's very high level first, but I think because we are all working in the trenches and then trying to tune parameters and all of this, we often forget what the high level goal actually is. And in the high level goal, obviously, is for machine learning to actually produce prediction, okay? And it fits into the scientific process as you can just see. I mean, the original scientific process is you have experiments like Newton dropping apples from a tree, and these experiments create observations. And now what Newton wants to know is, can I predict, you know, the energy of that apple or the ouch on my head for the apple, even without you doing the experiments? So experiments lead to observations. Observations give you theory. Somebody comes up with a theory. And the theory leads to prediction that actually should be so that you don't have to do experiments, or that you basically can generalize from those experiments a model. Now, what's new here, and because obviously the scientific method is old, what's new here was 50 years ago, 60 years ago, we started saying, hey, what if we put our theories, that means the models that humans came up with, into a computer and simulate, and then as humans we observe the observations that come out of those simulations, which is the predictions created by human models, and then we help refine our theory. Because if you, for example, drop the simulation of apples falling and you see like the apple going, you know, let's say to the upper right corner of the screen, that's not what we ever observe when we drop apples from trees. So that means my theory is wrong. But if the apples look like they look, actually they drop exactly like they do in nature, we would say, okay, yeah, that's probably right. So maybe my theory isn't so bad. That's how simulations work. And now what's really new, and that is in the last decade, and this is probably why you're all here, is that we say, no, we don't just give the prediction in and sort of handwrite the observation. No, we give the observation in and then have the model building be automatic and come up with a prediction, right? And so that's nothing else. When you do cat and dog distinction, right, in ImageNet, well, you give it cats, and dogs, and the idea is that the distinction between cat and dog is predicted by the machine learner, okay? And for me, my personal definition of data science is that it's the science of automating the scientific method. And why is it automating? Well, because if it's just the use of the scientific method, then for me, it's any other science. It's physics, biology, chemistry. The trick is that we now automating the process. But again, this is a larger discussion. Now, I'm intentionally coming from that way above there because I want us to keep this thread as we go through and think about experimental design. Because obviously, why is this important? Because we have a bunch of rules developed over hundreds of years of how good theory looks like, okay? And one of them is Occam's razor, for example, where we say a theory is good if it's A, consistent with the observations, so it predicts the observations, but B, is the simplest one. So the simplest theory that predicts the observations should be the one that's favored. And there's a whole field of philosophy called epistemology that talks about how this theory has to look like. But now what's interesting is, so if we use observation to create something to predict, which again in the human sense is theory, then it means that if you have machine learning, wouldn't it be prudent to actually apply all this knowledge from epistemology and Occam's razor, for example, to the models we're building, right? And my answer obviously would be obviously yes. I mean, you can disagree, but the lecture is about exactly that. The idea is our experimental design for machine learning should follow the same rules that we have developed over hundreds of years of what good theory is. And the result of this is a more complicated process. I know you just don't just go and say, oh, AlexNet works. No, it is a more complicated process, but the reward is that we have better explainability, more robust models, or, you know, on the bottom line, better theory created by a computer. Okay, that's basically where we go. So let's talk about this. So let's take this picture that we have and apply to it. How do we actually go through this scientific method, you know, traditionally? Well, traditionally, you have some person who is doing measurements, and those measurements go into a table. And so this is very important. From now on, I will refer to everything being a table. Okay, data, all the data you can ever think of, even temporal data, even images, audio, whatever you do, can be ultimately put into a table. Traditionally, it's not. You have WAV files or you have images, but you can put it into a table. And if you think about it, if you do an ImageNet experiment or you know, even something like a speech non-speech detection, you can put it into a table. There's a way to put it into a table. And so from now on, for this particular viewpoint, we will think of the table as being our data source. It's basically our sequence also will just be in the table from the beginning. So what we want to do is we want to have observations, we put it in a table, and then in the olden times, you would have a brain, you know, coming up, looking at the data, crunching, coming up with a bunch of things, maybe even using a computer for crunching, right? This is basically data science. And then coming up with a formula. With a formula, that is a model, right? So the formula is nothing else but a model. So you come up with a model that predicts what this table is doing. So for example, if your first couple entries are a variable, and then the last column is an outcome, you would be now, based on the next couple inputs, predict the outcome. That means the formula compresses the original table. So that is what we would do traditionally. And now all we do, the new version is, well, all we do is we replace that brain with computational logic, right? So instead of you know, Einstein sitting there, we want the machine learner come up with the same thing. So obviously one point that is currently highly discussed in machine learning is the point of reproducibility. And that actually has to be there, right? Because this formula, E equals mc squared, okay, that's more difficult to reproduce, but take any formula from physics, the idea is that you apply it to your data and it works, and whenever you do it within the constraints that are given, you can do it. And this is a big problem right now, is that this machine learning, often you have a paper, you try to reproduce, and it's very, very difficult. And I'm going to skip over this part, but I invite you to actually look at this in a more dedicated way, because we also often don't look at repetition, reproduction, understanding. We often don't have the granular experience of like, okay, so what's repetition, what's reproduction, what's understanding? This seems to be a spectrum, but it's just helpful to think about this in detail a little more just by using these examples. So and then we talk computer, the question is, well, what is repeatable, what is reproducible, and what is understandable? And in applying the theory would be, well, repeatable is if you take that finite state machine, let's say on a Docker instance or a virtual machine, and you put it somewhere else, well, that's repeatable. right? Reproducible, however, is that you can, from scratch, create the same experiment on your machine, right? So the paper needs to describe everything such that you can do it on your machine and you don't copy a Docker instance or a set of parameters from somebody else. And understandable is, oh, you can just do it even without reading the paper because you know exactly the mechanism and you just do it, right? And so we are very far away from, we are basically, whenever I ask students to like look at a paper and try something, you'll probably be doing the first thing, which is just repeating it. And then sometimes that doesn't even work. And so that is one of the big crises we have right now, is a reproducibility crisis, that basically we can't really reproduce, we can just barely repeat. So what can we do about this? Okay, so as I said before, I started thinking this from scratch. And when you start thinking from scratch, you start with very, very high level stuff. The first question that I asked myself is, okay, machine learning, well, learning, what is learning anyway? And then also, I know what machine is, it's a finite state machine for me. But the question is, what is intelligence, right? Where you go AI, right? So all of this though, nobody has to start thinking from scratch. There is a bunch of literature, a bunch of science that is not naturally in a computer science department or in a technical department, unfortunately. I'm going to hope to change that in my university, but the major point is Binet and Simon in 1904 created the definition of intelligence, which is the ability to adapt, okay? And the ability to adapt then has been recited a couple of times and also changed. So there are a bunch of papers here in archive and these newer where AI people try to rethink what intelligence is. I can tell you there's no need to rethink. This is a very crisp definition and it works pretty darn well. And also, funnily enough, there's a recent paper from Hutta, I think, from 2 years ago, where he's rethinking what intelligence is. He ends up with a very similar definition, basically rephrasing the ability to adapt. So in this particular thing, I completely urge not to reinvent the wheel, but to go with the definition that has worked. By the way, if you were taking a current intelligence test, one of these tests where they try to measure your IQ, it would be the Stanford Binet test. Yes, Binet is that name here from 1904. So the definition can't be so bad. Now the big question is, okay, the ability to adapt, and there's a whole lecture I can give you on what that means for humans. There's a brain adaptation, there's a genetic adaptation, there's other adaptations. There's a bunch of intelligence we naturally, or let's say culturally, don't see as intelligence, but genetic adaptation is intelligence. Having said that, we want to stay with machine learning. So what is machine learning doing? Machine learning, and I define this as machine learning, is adapting a finite state machine to an unknown function based on observations. So what we're doing is we're adapting the finite state machine to that table to represent that experimental table. And we will call from now on the finite state machine M because, hey, why not? And the table will represent as n rows of observation instances in a table with a header, okay? So that's actually very intuitive. Basically, each instance has a number of attributes, x1 to xm, and we will call the number of attributes m, and that is basically your assumed dimensionality. And f of x is your target function, your labels, okay? So where f of x is a column with labels, we call it target function. Now, right there is, we have to be careful because it may not be a function. It may just be x1 to xm, the same x1 to xm in one instance go to 0, and the next one, x1 to xm, go to 1, and then you have a not defined function. So for practical purposes, you will have to do that check. But for us right now, we will assume that mapping is always well defined as a function. And the output is obviously now a state machine that does the same thing, right? In the beginning, right now, all we do is we say we have to input x1 to xm, and the output is that target function. And of course, we will have to see, because that definition alone would totally allow for overfitting. It would totally allow for, all I'm doing is memorizing the x1 to xm each instance and memorizing each output, right? But that's exactly where I was going to go to. How do we improve on that? So we can also assume a weight. So by the way, the x1 here, the xi, so our attributes, we will assume element r. Now, first of all, important, real numbers don't exist in computers, but I put this on there because nothing will mathematically change if you assume real numbers or even complex numbers or quaternions. Nothing changes. In practice, however, we don't have real numbers, and you have this typical citation that people say, okay, but if my weights are real numbers, then all I need is one real number. That is true, but because we don't have real numbers in computers, we cannot do that. So let's not get confused with this, but I'm just saying your xi could be anything. But for now, we will say we only look at binary classification because that makes things easier. So what we'll look at right now is a binary classifier where we basically take this training table where, again, the data could be anything, but there's a dedicated row with f of x that is zeros and ones, okay? And what we want to do, is, because we want to do machine learning, is you take this table, train some computational logic, which could be a neural network or random forest or Gaussian mixture model, to take the inputs and give us outputs, but hopefully extracting a rule, that means generalizing such that we can extrapolate to unknown values later, right? So now, before we do that, first question is, how many state transition does n need to model? So is what is a state transition? A state transition is your inputs xi, right, x1 to xm, going to f of x. That for me is a state transition. And guess what? Because we set the f of x are binary, it's a binary state transition, right? So it's basically going from xi to each of the column is a state transition. And now I'm asking how many, and it's actually pretty clear. In the beginning, what we would need to memorize the table is we have n instances, so n rows of your table, forget the header, n rows of your table would need n state transitions. And of course, there's a bunch of theories that will give you this, like we can go with entropy and so on. But the trick is here. I'm going to skip those because we can go there, but it's much easier to just think about this intuitively for now. So there's a bunch of theory that will just count the number of state transitions there. So you can compress the table, obviously, using Shannon entropy. But for now, let's just think about this directly. So if we created a lookup table, then we would basically do exactly this. We can create a Python function, right? Def f of x, where x obviously is an array, and then x equals, and we basically do ifs. We say if x1 is this, and x2 is this, and x3 is this, blah, 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 until xm, return 0, right? And if f of x1 is this, and x2 is this, and so on and so on, until xm, return 1. That would basically be a set of if statements that memorizes the table. Now that is a valid definition, right? So that actually is, in this framework, right. You have a function that uses ifs or a lookup table to just model the original table. And what's interesting here is if you do so, then you need the number of rows as a lookup table, right? So basically you recoded your table into ifs, or you recoded your table into another lookup table or into Python or whatever. And that's great because it does fulfill this thought framework of machine learning, because this thought framework says all you need to do is convert your lookup table into a finite state automaton. You can also draw the finite state automaton, by the way, which is just arrows, right? From each x1 to xm to your f of x. Now, the bigger question is, how many state transitions do you need minimally, right? And so now the interesting question here is that in general, we cannot really answer this. I mean, we can calculate the Shannon entropy, but the real question of how small a finite state machine should be is called Kolmogorov complexity. And in general, it is the problem that we can't answer the halting problem. Now, the other thing though is that we know that this table will hold because it's just a function mapping. So there should be something else we can actually do. So in general, Kolmogorov complexity is not solvable, but we have a special case here. And so we can actually start working on this. This is not completely wrong to work on this. So I will give you a couple other definitions. And the most important one is this. So we will now ask ourselves quantitatively, what is, so we will now switch around and we'll go and ask ourselves that computational logic, right? Can we do something about it? And I say, again, in general, it's Kolmogorov complexity, but in our case, for binary classification, we could do something else. And we will now switch around and say, okay, if I have such a logic, right, what can I say about this logic? And I will say, well, one thing we can say is I call this intellectual capacity, okay? And the intellectual capacity is the number of unique target functions a machine learner is able to represent, okay? So that is just the number of target functions you could represent. That means for all possible given inputs and all possible given target columns, how many functions are there, and can you represent all of them will be the question. And right now I'm just saying, well, let's count the number of possible you could represent. And this is usually a function of the number of model parameters. Now, again, you could say, oh my God, this is a very complicated question, because if this is like a regression thing, oh my God, it could be a lot of different target functions. And the answer is, you're right. But that's why for this lecture right now, we will basically reduce ourselves to just binary classification. And now if you do binary classification, then of course we have a bunch of theory that helps us work with this. And people may know VC dimension, which is another thing which I'll talk about later. But if we go from this route, I will define something that I call the memory equivalent capacity. And the memory equivalent capacity is quite an important number that is really, really useful. And basically what I'm saying here is a machine learner's intellectual capacity, so the number of functions it can implement, is memory equivalent to n bits when the machine learner is able to represent all 2 to the power of n binary labeling functions of n uniformly random points. So basically what it is you take a table and you say you can put anything in, right? Anything. It could be uniform random, could be not, doesn't matter. But we know that the output vector f of x, so basically your column in the end, f of x, is only 2 to the power of n, where n is the number of columns, right? So the number of instances. For n instances for binary classification, all mappings that exist to that is just 2 to the power of n. And now the interesting part is, if you can represent all of these possible target functions, we'll call this the memory equivalent capacity of n bits. Now, why is this memory equivalent? Well, because that's how memory works. If you have n bits of memory, it can be in one of 2 to the power of n states, right? And so it's memory equivalent because right now, that only means we memorized, right? So by default, it just means we look at, okay, can you memorize that all tables, basically, of n entries? And what we call is not all tables, but all binary tables, okay? So what it means is, at memory equivalent capacity or higher, M is able to memorize all possible state transitions from the input to the output, okay? And M is our machine learner. You see, we haven't even talked about neural networks yet. You just talked to me about can we memorize a table, and we just gave it one quantity. Now I will work with memory equivalent capacity through the rest of the lecture. So if you're not yet completely like, oh my God, what does this do? Yes, we will develop an intuition. So the main trick is, again, just to repeat that, memorization is worst case generalization, okay? What it means is actually memorization is not generalization. Memorization means two things have to be identical. If you were memorizing cat images, it means the only cat you can ever identify is if you saw the image before, bit identical, right? But what we want to do is we want to say it's a cat image even if it's not bit identical to what we've seen before. So we want generalization. And now the question is, how can we analyze generalization before we do all the testing and validation? Can we do something earlier? Can we find a property so we can do this earlier? And that's also, again, the same thing as extracting that rule that we've been giving. If you deduce nothing from the data, the only thing we can do is memorize the observations verbatim. So we can memorize 6514, but we cannot do anything with this. And that means, wait a minute, that means using as many parameters as needed for memorization is therefore an indicator that the machine learner did not deduce anything. And we call this, we know the name for it, it's called overfitting, right? It means we memorized 2, 4, 6, 8, 10. We didn't actually extract the rule. And now that right there gives us something interesting. It means if we have a machine learner, whatever it is, that is below memorization capacity and still has high accuracy or 100%, that means that the machine learner will actually forget the original way it learned things. But if it's still able to predict, what it does is it will actually memorize a rule. So long story short, +2 is less memorization than 2, 4, 6, 8, 10. In fact, all even numbers are infinite memory, right? But +2 from a starting point 0 is not infinite memory. It's 0, we start at 0 +2, and now forever, for all infinite numbers, I can tell you what are the even numbers. And that's actually the trick. So what it means is we need to reduce parameters below the memorization capacity. And that will tell us that upfront, before doing train and validation, we know that we can generalize. Now we will work with this, okay? Now, that, by the way, right there leads to a formula of how to actually measure generalization. If memorization is worst case generalization, and we want the parameters in our machine learner to be smaller than those needed to be used for generalization, then, because we don't want to build a memory, then what we have to do is we have to ask ourselves, well, we divide the number of correctly classified instances. So how many instances can I predict correctly, divided by the memory equivalent capacity. So now it's pretty clear that if I can correctly predict as many instances as I can memorize, then I have a lookup table again. The lookup table needs to model n state transitions for n table entries, right? But if I don't have if I have something smaller than a lookup table, then my generalization should be much larger than 1, because again, I can correctly classify a lot more instances than I need to memorize. And so we want to get, and I measure this quite frequently now, actually every day, many times, the typical generalization you want to get for good machine learner is something like 50 to 1, okay? So if you want to go in and have like basically one parameter of your machine learner be standing for 50 rows in your table, that's what a good machine learner is, okay? And where you really know whatever test that you throw at it, it's a high chance that a parameter can pick that up again, despite the fact that the whole thing hasn't seen this before. But we have seen generalizations of 2,000 to 1 or 20,000 to 1. I've seen that, where you're like, okay, this is a model that works. I don't have to run a lot of validation on that, because 20,000 to 1 is pretty good. Now, when your model is closer to like 1, then you have a problem because you're overfitting. But even if you were not completely overfitting, if you like 1.2 or 1.3, you might still be in that Shannon. You might still be memorizing, but you could be lossless compression memorizing. So very important here, though, is that we don't really know how much memory lossless compression you can do. I mean, entropy gives us some limit, but you could well know. So what you want to do is you want to aim for, obviously, the highest accuracy, and that's completely still valid, on a validation set with the least amount of parameters, because that gives you the highest generalization, and that gives you the assurance that beyond your validation set, you can do well on a test set, because each parameter picks up a lot more samples that it models than if not. And then this is how you could basically, if you use the Shannon entropy, you could give you an upper bound for memorization still, but we'll skip that one. And what is interesting though, if you use generalization, you can keep the current approach with training, validation, benchmark sets, obviously, but you don't need any IID requirement, right? Because all I'm asking here for is the number of correctly classified instances. Number of correctly classified instances means that these instances have to be unique. But the whole trick with assuming IID is a little bit of a problem because we don't know the distribution, right? It's kind of nice to assume this, but it's even nicer to not have to have this assumption as of Occam's razor. And we also have, we can analyze machine learners in general with that formula without any distribution as assumptions. There's no, oh, let's assume it's Gaussian, or let's assume it's uniform. No, all we do is we count the correctly classified instances and divide it by the memory equivalent capacity. And now, of course, if we were in a room, your hands would go up and say, okay, but how do I get to the memory equivalent capacity? And that's obviously, this is going to be the new art, because we need to find the memory equivalent capacity for different machine learners. Now, I am going to tell you how to do that for neural networks. And before that, I'm going to tell you really quickly how to do it for a binary decision tree, because it's trivial. The depth of the perfect tree is the memory equivalent capacity of a binary decision tree. And obviously, that's how memory works, right? So you have a perfect tree, and that depth in bits is your binary decision tree, because your perfect tree models 2 to the power of n being the depth of the tree, states, so log 2 of 2 to the power of n is n, and here we go. That's how you get the memory equivalent capacity of a tree. Now for a neural network, that's a little bit more tricky. How to get there is more work, but I'll show you. And I also, again, want you to see the app that we have on the web, so you can take a look and do this by hand and try it out. So, you will see that this then created an engineering discipline, and all supervised machine learners have a memory equivalent capacity. So yes, all supervised machine learners can overfit, and we should be able to measure that point of overfit by measuring when is it memorizing, right? And it is computable and measurable. And this by itself, by the way, allows for task-independent optimization of concrete network architectures, learning algorithm convergence tricks, and we can approximate the capacity requirement given input data. So let's do this. So now I'm going a little faster. Hopefully people have seen this a little bit, but also you always feel to ask questions. So the way for me to look at the capacity of Perceptron is, there's a couple previous work. One is McKay, which I cited already. The McKay book, chapter 40, is absolutely what I recommend. He goes graphically through how he derives capacity for a Perceptron. It's a really nice read, not an easy read though. So take a weekend, if you happen to be stuck at home, it's a good book to read. It's all online as a PDF, so no need to buy anything. Even though I would recommend to buy it because it's just a very nice book, and supporting the author is always a good thing. But so here's what happens. So we have a Perceptron. What does a Perceptron actually do? Perceptron calculates the dot product of the inputs of our table xi and of some weights, so uwi. And then with that dot product sum, we ask ourselves, well, is this below or above a threshold? If it's below a threshold, when we do nothing, it's 0 output. If it's above a threshold, we fire. Now this gives us what's called a step function. You see that step function here. And obviously the problem is our current training methods don't allow for step functions because we need to calculate a derivative. So we use all kinds of step function surrogates. For example, sigmoids, or the later one is the ReLU, okay? But for our mathematical analysis, we'll find out later that whether we use a ReLU or a step function or a sigmoid or whatever we do, we can just work on the probabilities that the output will be 0 or 1, and then it doesn't matter at all whether we use a step function, because the maximum probability that it could be 0 is that it's basically 0.5 probability. So it's equiprobable 0 or 1 would be the exact symmetric step function, and it could just be less. But the interesting point is, if you just look at the probability of the output being 0 or 1, and the highest probability would there be equiprobable, we don't know if it's 0 or 1, then basically what we can say is, well, the information we gain from an equiprobable output is maximally 1 bit, okay? So that's actually how we will operate. We will say, who cares about the target function? For us, it doesn't matter. We only care about the probability of the output. And the information we can gain is log 2 of that probability, which is 1 bit maximally. So, and this is true for all different target functions. We don't care. Point is, it can only be less, right? So if you have a target function that's not symmetric, or that there's some shaping here, like an arctangent or something, or ReLU, and it turns out it doesn't matter, your probability is the same or less, right? However, if you have an identity function, then obviously it's linear, and f of x is x, then we can't really have a probability that it's 0 or 1. So let's just skip that one. So whatever we will talk about right now is if you have some kind of thresholding nonlinearity. By the way, if it's linear, like the first one, would be a different lecture. You can use Kirchhoff's laws from electrical engineering to completely model any neural network. Done this before, it's fun. But not what you want to look at right now. Let's look at the nonlinearities. So this has been done before too. So how many how many functions can you model using a single perceptron was asked first, I think, by Minsky in the 50s. And he said, well, we have a linear separation, right? So we should take a look, linear algebra, and just see if you have, for example, a unique rectangle, a unit rectangle, like here, what are the linear separations that we can go through? And again, this has been done before, and it leads to a very interesting discussions. For example, which Boolean functions can you model with one neuron? And Marvin Minsky was super angry at the fact that actually one neuron with 2 inputs can model all 2 to the power of n Boolean functions of sort of n states in the end, except 2, right? So of the 16 functions you have of 2 variables, or of 4 2 to the power of n, 4 output rows. So the output column being 4 rows, it's 2 to the power of 4 is 16, or of 2 variables is 2 to the power of 2 to the power of 4 is 16. You can only model 14. The 2 you cannot model with the perceptron is XOR and not XOR, okay? And we've seen this before, and then McKay explains this. So in McKay chapter 40, you go and say, why don't we use information theory? Why don't we go and say, okay, we understand this neural network as an encoder, right? So a single perceptron gets labels and encodes the labels with the data as weights. And then as we try to decode, we take the weights, we have the weights and the data, and we try to reproduce labels prime. And it turns out the information theory there tells you that you can totally do that for all functions except 2. In fact, there's a neat curve that comes out. So this curve is a very universal curve, and I'm going to spend a little time to explain this. So it turns out if you model the number of parameters that a perceptron has as k, and then n is the number of points you want to model, okay? So in this case, for binary functions, we have 4 points to model. And then k would be 3 parameters, because you have 1 weight each, weight 1 and weight 2, and then you have a bias, okay? So n is, in this case, 4, because we have 4 points, and k is, in this case, 3. Now, for n case 3, the answer is 14. And there's a whole function that was developed. He calls it the T and K function, which is T gives you the number of thresholds that you can create for n points with K parameters in your neural network. And now, if you look at this information theoretically, you will find out that if the number of points you want to model, and again, this is binary classification, the number of points you want to model is the number of parameters, you can always do it, okay? So all possible, the probability of the perceptron to model your function is 1, okay? So the moment you have all function, you have the same number of parameters in the perceptron, then you have points to model, you're fine. Now that's interesting because obviously for and or and so on, you still have 4 parameters here, but it turns out, and unfortunately I don't have a whiteboard, I can show you how redundancies would actually model whatever, you could compress whatever table for all 14 functions to just 3 or 2 or 1 input, right? But XOR and AND, you cannot compress. You need all 4 points. You need to model all 4 points, okay? So what it is if you don't know that you can compress, if n equals k, you can actually model everything, okay? So for n points of a table, if you have n parameters in your perceptron, for binary classification, you can model all. Now, more interesting is what happens if you go beyond. So you have less parameters in your perceptron, then you have points to model. And it turns out that what you do is you look at the quotient n divided by k. Now, n divided by k is 1, obviously, if n equals k. But it turns out that if n goes to infinity, so if you have a large number of attributes, the curve looks like this. What it looks like is n is the number, if n is twice the number of k, you have still a very, very high chance to be able to model it. But then at some point, it just breaks down. It just goes to almost 0. Obviously, that 0 is also only reached asymptotically. But 50%, and that's a hard number, 50% of all functions can still be modeled with a perceptron if n equals 2k. So that means if you have twice as many points as parameters. Again, this is all for binary functions. I derived the same formula for multiclass, and it looks quite different. But it makes total sense the moment you do it. I'm not going to present it today, though. So now that's all cool. We know how many functions can be implemented. We know the capacity of a perceptron. So the capacity, information theoretic capacity of a perceptron is twice the number of parameters. Or basically, the memory equivalent capacity would be n equals k. So that's the major point. Because memory equivalent capacity is saying, for any random points, can I model it? And that means the number of parameters equals the number of points that I can model. And so when you have the number of parameters equals the number of points, you can model all functions. That means you have n bits of capacity, because all functions means all 2 to the power of n different states of your target column in your table. So that means the memory equivalent capacity of a perceptron is the number of parameters in bits, okay? Now the bigger question is, oh my God, 1 perceptron. I never deal with 1 perceptron anymore. What the hell? We need to go to networks. But before, I see 2 questions. Before, when we were talking about nonlinear activations, how do you model probability with only 1 bit? Since the probability is a real number. So to go from bits, the probability is indeed a real number in 0, 1. That's completely right. But to go from the probability between 0, 1 and bits to go from probability in real number, from real number to bits, you take the log 2, okay? And obviously that is again a real number. But what we want to know is what's the maximum information that can come out of a perceptron. And maximally, it could come in 1 bit. And this would be the case when you have 0.5, 0.5 for 0, and so 0.5 probability for 0 and 0.5 probability for 1. Okay, so that's just the information content of the output of a perceptron can maximally be 1 bit. Does larger capacity naturally lead to overfitting? How do we know that the capacity is being utilized? That is a very, very good question, and I'll go at that later, okay? The point is, larger capacity would lead to overfitting if we had perfect training. Unfortunately, the training method we use, backpropagation, is a Monte Carlo method, and so that means we lose a lot of information. We don't go through all the degrees of freedom of each parameter, and so that means we have a problem there. That's where the theory has shortcomings, and we need to come up with something else before we go there. So that's a very good question. Hold that thought. Let's get to that later. For now, we assume that we will go through all states of all attributes of all parameters. We will assume perfect training, and then with perfect training, you can actually go and get to this curve. If you have imperfect training, even of your single perceptron, you won't get to this curve. And in fact, I will show you this curve with imperfect training. What usually happens is, and you see my mouse cursor, I assume, what usually happens is that not all functions can be implemented because training just doesn't get there. And that means the curve has about the same shape, but it caves in earlier, okay? It looks like this, it caves in earlier. And for me, it's a quality measure of how close you get to that curve. Because the better your training, the more you can actually get to that curve. So that becomes an engineering question. Can you engineer training in such a way that it gets very close to that curve? Okay, so now I wanted to go from one perceptron to many perceptrons. So this is not just one perceptron, this is the typical multi-layer perceptron network, right? And so how do we go from one perceptron to many perceptrons? And this is now the main trick of the lecture. The trick of the lecture is to say, well, first of all, not all networks look like this. When I built a theory for this, it needs to also explain a typical MLP that looks like this, or a shortcut network that looks like this. Yes, this is called a shortcut network. And of course, Facebook, or Microsoft, I forgot, reinvented this and called it ResNet. What it does here is it has connections that go directly from the input to a further layer. And of course, we have ResNets all the time when we go from some input to the next layer. And we need to explain that too. And it can become quite complicated. But here's what's interesting. As I said to you before, I know the capacity for a single perceptron. So the next question is only, how do we get to the combination of capacities? But since we only look at memorization, it feels to me like we only have to look at what if we combine memory cells, and it becomes the same as basically looking at these networks as circuits. For me, these networks are now electrical circuits of memory units. And guess what? That's a solved problem because we combine memory all the time. I mean, I know latest models of laptops, they don't allow you to put memory in anymore, but in the olden days, we would buy memory cells and just put it in. And sometimes we combine it in a way so we have more memory, but also in other times we combine it in a way that we have error correcting codes and so on and so forth. So how to combine memory is solved. So let's just apply this theory. And it turns out, then it also gets to the point where we calculate in bits. And it turns out you get to 4 rules. First of all, again, we calculate in bits because I just explained it to Michael that the maximum output of a perceptron is 1 bit. So that's rule number 1. The maximum output of a perceptron of a single neuron is maximally 1 bit. If you change your activation function, it can be less than 1 bit. If you change training, it can also less than 1 bit. But for now, we'll talk about the maximum. The maximum is 1 bit. And now, we also know from McKay, and I just derived that using that curve, is that the maximum memory capacity of a perceptron is the number of parameters. Remember, the memory capacity is the point where we can implement all functions, okay? And that is the n equals k point. And so we all have to say, well, n parameters when n equals k, we could implement all functions. And that means is we just count the number of parameters. By the way, the bias just counts as one parameter, okay? So a single perceptron, a single neuron with 2 inputs and 1 bias has 3 bits of memory capacity. It can guarantee to model any binary functions of 3 inputs and 1 output. Okay, so basically 3 points of input and 1 output. So that's the point. Now the dimensionality of the inputs is given in a perceptron by the number of inputs in the perceptron. That's kind of interesting that this is, well, right there defined. But these are the 2 rules we already explained. So the output of a perceptron is 1 bit, and the maximum memory capacity is the number of parameters. Now, what happens if you combine neurons, right? What happens if I have 2 neurons? If I have 2 neurons, then it turns out the capacity of perceptrons in neural network is additive, okay? So it turns out, we've done this empirically, and by now I've also derived it. McKay already speculated that this will be true. You just add them. And later on, we actually did experiments and confirmed it, but also you can mathematically see this. Unfortunately, not so easily, because you have to also guarantee that there's an output neuron that can always combine these perceptrons. And you can actually guarantee that, and that's because this output layer solves as a demultiplexer. But we don't want to go into demultiplexer theory right now, but you can do it for showing this mathematically, you can just go there. So the major point is the maximum memory capacity of perceptrons in neural networks is additive. So what it is it's pretty clear. If I have 10 bytes of RAM and I add another 10 bytes of RAM, then I have 20 bytes of RAM, right? So if I have 1 neuron and I add another neuron, then in that first layer at least, I have twice the number of capacity. So you can just go with that, okay? But there's a problem. If you layer deeper, we have another phenomenon. It's called the data processing inequality. And there's a whole book, and I'm sorry, but I don't think you need the book. It's pretty clear. So here's what happens. If you have a layer that depends on a previous layer, it doesn't matter that you have 10 bits of capacity. Let's say you have 2 layers combined, and the first layer has 10 bits of capacity, and the second layer has 10 bits of capacity. It doesn't matter though that the first layer has, the second layer has 10 bits of capacity, because the second layer, the second hidden layer, is dependent in a typical deep learner on the first hidden layer, right? So what it means is the output of the first hidden layer gives you the number of bits. And usually it's not the same as the capacity. It's usually something like you have 3 outputs that gives you 3 bits, right? So if you combine the outputs, you have 3 bits of output. Now, if you have 3 bits of information and you put that into 10 bits of memory, do you get 10 bits of information? No. If you have 3 bits of information and you put that in 10 bits of memory, you have 3 bits of information still. And that's actually what this is. So if you combine layers deeply, then you have to keep track of the output, because you will never go above that capacity. So you have the capacity, but the reality is you're not using it. So you might as well just count just the output capacity. And this is basically how I'm suggesting we do it. Here's an example. So again, 1 perceptron, 3 weights. The memory equivalent capacity is 1 bit plus 1 bit plus 1 bit is 3 bit. Now let's look at this one. Here we go, 1 bit plus 1 bit plus 1 bit is 3 bit again. And here's also 1 bit plus 1 bit plus 1 bit is 3 bit. So 2 times 3 bits is 6 bits, right? 2 times 3. But now the output neuron is different, because by itself, sorry, we're missing the B3 here. Okay, there's a B3 in this. By itself, it has 1 plus 2 plus B3, 3 bits of capacity. The problem is, yes, I have 3 bits of memory, but reality is I only have 2 bits of output, because the output of a single perceptron is 1 bit each. So that means 1 plus 1 is 2 bits of output, and that means that in total, actually, I don't have 9 bits of memory equivalent capacity like I could have. I actually end up only with a minimum of 2, 3, which is 8 bits. Again, sorry that I'm missing the B3 here. So there's a bias in here. So what happens is I need to just count it this way. So let's do it in a better example. So this is a typical, very simple deep learner. And I say, okay, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 is 3. So the first layer, assuming there's no limitations in the input whatsoever, has 6 bits of capacity, 2 times 3. But now we are outputting 1 bit each from each neuron, right? So now does it matter that we multiplex? No, it doesn't matter, because B1 outputs 1 bit, and that same on-off state goes to this, goes to the first and the second output. But a different on-off state goes to the third and the fourth output of this layer. So what it means is that in general, we have 2 bits out here. So because we have 2 output bits here, it doesn't matter that we have a lot of memory here. This is 3 bits of memory each, we get it, so 6 bits again. But the reality is we are constrained by the 2 bits of output. So it turns out that this is 6 plus 2. And now we have another 2 bits of output. So it's 6 plus 2 plus 2. And then that's it. So the memory equivalent capacity of this whole network here is 10 bits. What it means is this network can model 10 rows with binary classification, basically with binary labels. Whatever rows they look like, you can memorize them. But if you do more than them, more than 10, congratulations, you generalized. Okay, and that's something you can actually try out in the app that I showed you in the beginning. Let's go to a question. Why is the first bit counted? Is that considered information as opposed to memory? I'm not sure what you mean with first bit. Could you clarify? So the first bias. Yes. So the bias is always counted as a parameter. And the reason for this is because you could make the bias 0 and then replace it by a weight with a constant input 1, right? And the weight would just be your bias. So basically, it turns out the bias just counts as a weight. It's just what it is. So the first bias is counted as 1, 2, 3, 1, 2, 3. Each layer independently has the same. It would be 1, 2, 3, 1, 2, 3. And also the output would be 1, 2, 3. So the absolute maximum, and without regarding the data processing inequality, would be 3 plus 3 plus 3 plus 3 plus 3, which is 1, 2, 3, 4, 5. 5 times 3 is 15. But you don't get to 15 because the 2 outputs limit what this can store, right? It's, as I said, you have 2 bits that you put into 6 bits of memory. That doesn't mean you have 6 bits of information. That means you have 2 bits of information. So these 2 bits can only lead to further 2 bits, okay? But biases just count as weights. Now, what about this one? This one was the interesting. I said the theory needs to explain this one, and it turns out it does. So what it does here is 1 bit plus 1 bit is another, and another bias gives us 3 bits. And then this perceptron is interesting. It takes the full bit from that output, but it also has direct connections to the initial input. And that means there's no data processing inequality. This second perceptron makes an informed decision, okay? An informed decision. It basically looks at the original problem and also asks a friend, right? And informed decisions are usually the best ones. So basically, the point is, that's also what happens. You end up with absolutely using every single bit of capacity you can in this network. And this means this network is much more efficient than a regular multi-layer network. And we know this is exactly true for resonance. Resonance are a lot more powerful. But it also means our training method needs to be able to handle this information density. And this is why resonance are actually harder to train than regular neural networks. But the major point here is that this gives you a complete explanation of how this works, because you get 1 bit plus the unconstrained input and so on. So per number of weights, this is the most efficient network, or per number of neurons, definitely. 2 neurons, 7 bits, That's pretty good. Now, we wanted to ask ourselves, can we create the same curve again for the same McKay curve with n divided by k equals 1 and so on for a neural network? And how does it look? How does it change it? And it turns out, and you can show this with the data processing inequality again, actually it doesn't change. So for a 3-layer network, the curve looks the exact same way. It goes further and further to the theoretical McKay curve if the number of neurons in the middle layer increases. Other than that, it looks to the exact same curve. So the memory equivalent capacity of a 3-layer network is just exactly constant, like n bits, where n is the number of parameters for a 3-layer network. And of course, once you go above that, it can compress better the more parameters you have. So now this is the theory, and this is actual practice. This is an actually measured 3-layer MLP. That's scikit-learn. Most people know this. You can just say pip install scikit-learn, and then actually you install scikit-learn. You install scikit-learn, and you can use that MLP. And we did that, and we measured it out, and it's a bunch of measurements. I have them all on GitHub. You can repeat them. It's all reproducible results. And these measurements give you basically that curve from McKay in a 3-layer MLP, and it shows exactly this way. So how to do those measurements? Well, the way we do those measurements is we create uniform random input points, and also obviously uniform random tables, and we go through all combinations of them. And in theory, you have to go through all combinations of tables, but it's because obviously we know that some tables are easy, some tables are hard. We restrict ourselves to the difficult ones, which is the uniform random ones. Yes. Does this magic cap explain the discrepancy between this high VC dimension but good observed performance of large neural networks? Yes. I love the question because this is exactly the right point for these questions. So VC dimension. So here's what I first of all recommend everybody to do when they have a VC dimension question. Please go to the original paper from Vapnik and Chervonenkis, okay? And when you go to the original paper from Vapnik and Chervonenkis, you right there see his own confusion, okay? He explains VC dimension in a really good way. He says VC dimension is basically the maximum dimensionality, the maximum number of points in a set that a machine learner can implement all functions for, all binary labelings, right? And so that's very, very similar to my memory equivalent capacity, except it's not. So here's the big problem. VC dimension says, give me a set, and then we'll analyze how many functions we can implement for that set, right? And what it does is, for example, it says the VC dimension for the sinus curve, for sinus is infinite. That is true. The VC dimension for sinus, and that's his second example right after his definition. The VC dimension for sinus is infinite if and only if your points are distributed in such a way that the sinus can make a perfect cut. But for uniform random points that are in any position, there is no infinite. For uniform random points that are in any position, the sinus is probably be able to get the first 2 points, and then you have to have a new sinus for the next 2 points. And that's actually not explained in the original paper, and that creates the confusion. So, given a set, the VC dimension of a perceptron, the best possible set you can find so far, and we have found, is Peter Bartlett n log n. What does that mean? If you arrange your inputs in a checker pattern, then you can find linear separations that go diagonal, and that means you can separate n log n points with n parameters. That's kind of cool, right? So for that concrete structure, you can do it. And you can even do it if you add a little noise to the points. But if you were able to do that for any set of points, we would have universal lossless compression. And that obviously would be, that means I can model n log n points into n parameters, and then I take those n parameters and model them again and again and again and again and again until I model whatever set I put in one parameter. How cool is that? that can obviously not work. So basically what it means is VC dimension is asking the question, for a concrete structure, what is what I can model with the machine learner? So what is the maximum that I can model? So if my points are in the exact right position at period length, sinus can with one sinus parameter, I can separate an infinite number of points. So if my points are in a checkerboard, even noisy checkerboard pattern, basically class 1, class 0, class 1, class 0, class 1, class 0, in a checkerboard pattern, little noisy, I can find a neuron that can model n log n points just with n parameters. But that's not what I'm asking. What I'm asking is, wait a minute, I don't know what the structure is because I'm doing machine learning, I'm giving some data set. So what I'm asking is, what is the number of parameters so that I can model all sets, okay? And so basically the VC dimension proof or for sinus and also for the single neuron fall apart at the moment where you basically say, okay, no, I'm gonna give you completely random points. So then the sinus is not able to do infinite. And then also a neuron needs to be n parameters for n points, okay? And yes, that is a very, very important question to ask. And that is actually where the discrepancy comes. If you actually now just add the VC dimension n log n for deep neural networks, then you get this huge capacity. But that would mean you need to basically put in this checkerboard pattern. Now here's what's interesting, and this is not wrong, by the way. The first layer only is where you need my capacity, because in a second, third, and fourth layer, it's your choice of how you model. So the first layer could totally map whatever input points to a checkerboard pattern, if that's possible. Obviously, it's not always possible. But you could say, haha, I do that. And now everything is checkerboard pattern, so we have super huge capacity. And you would be, yeah, that's right. I would be, yes, this is true. If you can manage to do that, good luck. But here's the problem. You would have a training method that's pretty freaking perfect. Because for that mapping to happen, you have to be absolutely knowing what you're doing. And you're solving a packing problem when you do that. And solving a packing problem is absolutely exponential or NP complete, right? Even bin packing is. So the point here is that there is a discrepancy between the high capacities you get, but first of all, you have the information, the data processing inequality, which I just showed limits you, so that even if you assume you have the perfect n log n mapping, well, you only get 2 bits in. So it's n log n of 2, right? So n is 2, it's only 2 bits of information. And the second one is you don't have perfect training. That means you don't even get to the amounts of information that I give you. Of course you don't, that's already far away from the VC dimension, right? So you don't even get to what I'm telling you because of training. So yeah, that's how you explain the discrepancy. Hopefully that makes sense. So given data and labels, now the big question is practically, given data and labels, how much extra capacity do I need to memorize the function? And so we developed a bunch of heuristics, and I think we're running out of time, but I really wanted to answer that question because it's a very core question. So I developed some heuristics. It's in a paper of basically saying, okay, if we created a network, we call this fast match in speech. If we created a network where all weights are 1 and we only train the biases, we can do so in n log n time for binary classification. This is the algorithm. And then we get a dump network with a bunch of parameters. Dump because it's learning restricted, right? So it's a learning restricted network because we don't train the weights, we only train the biases. And it turns out that's basically a hash table. And it turns out that hash table gives you an approximation of first of all, it gives you a perfect memorizer for your table. But also you could ask yourselves, with training, now that I allow the weights to actually wiggle around and train, how good could you become? And what I say is, yeah, well, guess what? It becomes a B tree. A B tree is logarithmic in size of the thresholds you need to model a data set. And that means it's log of the number of thresholds. And that gives you an expected memory equivalent capacity. And that expectation is pretty good. This is an old table. I've done this on a bunch of couple data sets. We tested the thing on 100 OpenML data sets, and we were pretty good in our predictions. And in fact, we then used neural networks to model the thing. And of 100 OpenML tasks, 88% we were modeled better than the actual publication behind it. So we beat the state of the art in 88% of the cases. This is not yet out. This is not yet a result that you can look up. I'm telling you this because it will come out. We will publish this. But the major point is that stuff helps you size neural networks. And as you size your network, you get a better theory. That means a better model. And as you get a better model, you can actually predict better. And that's the whole point, right? The biggest problem with training, the biggest problem we face with this theory is training, because the training we're doing is pretty much Monte Carlo. Again, McKay chapter 41 actually will explain you this. You should totally take a look. So what we want actually is we want different training methods. Now that we know the capacity, we should actually develop new training methods that go to the brink of the capacity. And they should pretty much work like charging a battery, to be frank, because you want to have each neuron charged fully and not use the neurons only halfway. And the biggest trick here is not to assume some architecture first, but to build the network up incrementally. And so that would basically be the way to do that. So we need to have different training. If you want to do, if you want to take a look, again, we run out of time, how this really works in the real world, what turns out is if you were to start with a big network architecture and you were to cut neurons, bum, 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 obviously your probability of memorizing your table will decrease this way. Now this curve I've drawn for uniform random data. Now this means all I can do is memorizing, but it turns out if your data is not completely freaking random, if it's something you can compress, then this curve will actually stay stable for a long time. And then you get to n-approx. N-approx, it should be actually called k-approx, I'm sorry. K-approx is the point where you say, this is the amount of parameters I need. And here's the other thing. If you look at your validation set, your validation set will go up. It will start with, we don't know, some randomness, maybe 50% because it's binary, and it'll go up and it meet exactly at the k-approx point, at the point where you're not memorizing, you're generalizing, but you're generalizing to both the validation set and the training set. And then afterwards, as you cut parameters further, you basically go down here. And this is this sort of capacity reduction while training, I call quantization, and it's exactly what happens when you do lossy compression. And that's why it looks like this. It takes me a little longer to explain this curve right, but basically what you want to do is you want to find the trade-off between accuracy and generalization, because that gives you perfect prediction. And I can also tell you that not obeying this, going and just using some architecture, it's a waste of money, energy, and time. That's the reason why we have all these hyperparameter tuning, because we don't know how things work. We want to build things like batteries incrementally. It's bad for the environment after all. And the less parameters, the better generalization. Each parameter can pick up more stuff. The higher adaptation per parameter, right? It's just intelligence, the ability to adapt to change. And the higher the chance an unseen instance can be predicted correctly, okay? I gave another talk on just that, so that takes also a little bit to internalize. But what I can tell you is obeying Occam's razor does help with adversarial examples, and it's a whole other explanation. But what I want you to do right now is just keep it to the capacity. I just want to give you an outlook at where this leads. It leads to a bunch, it's a whole can of worms we're opening the moment we understand capacity. And so, however, I will invite you to understand capacity first. And the way to do it is to play around with it. So we have Axel is maybe even on. He and Henrik and students before derived out of the TensorFlow playground, what we call the TensorFlow meter, and it gives you all kinds of interesting stuff to play around with. So you can build a neural network. As you build your network, it gives you the memory equivalent capacity. And it'll also estimate the demand for a data set you have on the left. You can upload your own data set. You should actually just click on this. We're sharing. Here we go, right? That's the whole thing. And it gives you your own data set you can play around with. So we can add something here and so on that increases. You can play around with your own data set or can use one of these. And as you model your network, you can actually find out various things, and you press play and it's trying to train it.
Here the screen is blank.
Hmm?
The screen is blank. I don't see anything.
Oh, the screen is blank. That's bad. Let's stop sharing and then let's try this one more time. Do you see now?
Yeah.
There you go. So this is basically, first of all the rules are implemented. So you see memory equivalent capacity here. And then all the rules as you build your network are implemented. They just do the math for you. You don't have to do it by hand. And then you can choose a data set, right? And then the capacity estimation algorithm that I show on the slides that I didn't explain in the lecture is used here. And of course, this one is easy to separate. And then as you press play, it'll actually train the network. You can look at all the weights here, right? You can also upload your own data set. If you press plus, okay, that will be this. But if you take something more interesting, like this one, right? So this basically is saying that we would need 12 bits of memory equivalent capacity. So let's try to model it with less. And you'll see, yeah, this is difficult, right? So what we do is we add 12, and then we should be able to do it. And by the way, I can tell you that I like ReLU the best. And of course, it also depends on the initial condition, and training isn't perfect, but it'll eventually get there, okay? If we add a little bit more capacity because our training isn't perfect, then it'll get there faster, right? Sorry. It's right now acting out. Here we go. So let's do this. Okay, it's not getting there right now. I don't know why. Because I'm, well, almost, okay. But you can play around with this. You can add noise to the data set, which then obviously increases the capacity demand. You see that? It goes up. You can work around with the batch size. You can do ratio of training and test data, where test data is going to be validation set at this point. And you can do you can work with the learning rate, which I call gradient scaling, because learning rate is something where you actually go and say how fast does the machine learn. And then you have regularization. You can play with all of this. And what I usually students ask me is, wait, how do these not make any difference? The activation functions only make a difference for training. They don't make any difference in terms of memory equivalent capacity. And so you can actually figure this out by looking around with this. And the most interesting structure to learn is a spiral. But again, you can create your own. And you can regenerate the data set at any time. There's this cheat sheet that I put out earlier. And then there's also the another lecture on how to use this app on here. So you can take a look. Yeah, I think we're running completely out of time. But at least I hope to have conveyed the idea of capacity, how important it is. And I totally invite you to play around with this. And you'll be surprised, because of all the networks in the beginning, AlexNet and, let me share the slides again. AlexNet and oops, give me a sec. AlexNet, all these networks are 10-fold too big, sometimes even 100-fold too big. It's just what it is. Yeah, so, and then if you want to learn more, go to this tiny URL, because that's my experimental design for machine learning class that I teach at Berkeley, and actually increases in students, and I just got a budget for it. I'm really proud of this, that this becomes a real class. It used to be just a seminar. So it's still just a seminar from last semester, but we're getting better and better. And there's homework there. Obviously, I cannot tell you to do some homework. That's Bixa's prerogative. But take a look. If all of the homework is not there to test you, all of the homework is there to deepen that knowledge that I just gave you and to help you with understanding, for example, why it makes sense to measure things in bits in a machine learner, and various just hopefully fun exercise. I will tell you that I never graded this homework. It was mostly meant for the understanding. And one important thing in the homework is it always emphasizes the bottleneck. So whenever you do machine learning, you have to ask yourselves combinatorically, where is the bottleneck? And that's interesting because you could have a huge table, but if it's a binary classification, then really all the number of functions there exist is 2 to the power of n, where n is the number of rows in your table. And even though there could be huge dimensionality in the input, and there could be very high complexity, it could be strings, combinatorical explosion and what the input can be. Yes. The reality though is if it's binary, that's all the functions you can have is determined by that output column. And for example, there's a whole bunch of exercises that just makes you, for different problems, find these bottlenecks. And I think that's a huge confusion that we have in the machine learning community right now, that people try to model something that's not the bottleneck. Anyway, I'm way over time. So I'm here though. If you have questions, I will just stay online. If I can, I don't know, Biksha, can I, or do I?
I think the students will actually have to go to other classes, but this was very fascinating.
Okay.
So I'm going to post the slides and of course the video on the class website. I expect that they'll probably hit us on Piazza, in which case I'll forward the questions to you guys.
Yeah, okay. And I mean, I can stay on if I don't block anything in case people have questions. But also, you can email me. I wonder, I can obviously also just open my own Zoom. I have a Berkeley Zoom. And then you guys can ask questions if that's useful. So whatever makes sense, right?
So I suggest, Gerald, that you actually post a link to your Berkeley Zoom, so I can stop this recording over here.
Okay.
And
cool.
And if people want, I'll post that on Piazza, and they can ask you.
Perfect. Let's do that. So I stopped sharing this. Also, Axel just put the newest version. So the TF Meter app, we have a new version, and that allows you to actually play with resonance. You can actually do your own connections. Super cool. And that he just posted. But let me give you my own Berkeley Zoom, which I actually have to find out myself because I have so many Zoom addresses these days.
So anyway, I'm going to stop this recording right now.
Please stop the recording. Yeah.